Hi, everyone.
Hello.
Just wait a couple more minutes for folks to gather.
Hey, Srijit.
Hi.
You should be able to share your screen at any point.
Okay. Let me share.
All right.
Can you guys
Okay.
see my files? Yeah.
Yeah.
Okay.
So our guest today is Srijit, who for some inexplicable reason has another meeting scheduled on the usual Friday 8 a.m. slot. So we're using the Bow slot, and hopefully you'll also talk about the bunch of wires along the way. So it's all yours. Thank
Okay.
you.
Okay. Good morning, guys. Today the subject matter is on the chiplet interconnect test and repair. I know this group does a lot of work on the design side of things. In my opinion, this is also an important thing that we need to consider, because at the end of the day, if we put things together and things don't work, and we cannot certify it to be good and robust, then we have not achieved our goal. Okay, so this is I'll be preaching to the choir if I tell you that the chiplet revolution is on us. You guys are doing some wonderful work, and we really looking for everything that you're doing is basically trying to get these things eliminate all the kinks so that we can really achieve our goal. Okay, so this is a presentation I made at the IEEE Asian Test Symposium as a keynote there, and some of you may have seen it. Okay, but what I would like to do is that rather than me just speaking and you be a passive listener, I would welcome questions during this presentation so that we can make it much more interactive. Okay. The next two files are basically a bunch of references from which I drew the material. Some of it are basically in the from press releases, and some of these are some papers that I had published in the past. Okay. So, okay. And with that, let me start with this.
Oh, Srijit.
Yeah.
Sorry, I realized I did you a disservice. For everyone else, Srijit's a super old friend, which means we're both old, but that's a different story. But Srijit has worked on test for quite a while, and then he also came in and gave a talk to us on the work he did on Ponte Vecchio and everything else. So this is he's got sort of both the theory experience as a professor and practical experience at Intel for many years in this space. Sorry about that, Srijit. Thank you.
No problem. Thank you. Much appreciated. Okay. I'm not going to spend much time here. This was mostly for the test folks to tell you, why we want to do the chiplet-based design. But the thing that I'm going to do is use some terminology here, because there might be certain things in this presentation terms I use that might be familiar to some of you, or you might be using a different term to refer to the same thing. Okay, so so that is I'm going to refer to this interposer as a passive, which is a passive die or an interposer. Okay, and then there is a package substrate. Okay, and if you look at and then if you stack dies on top of each other, we refer to that as a 3D interconnect. Okay, and then there is a 2.5D interconnect version that uses the passive interposer, where you place dies next to each other. Okay, and then there is also the interconnect that is used through the package substrate. An example of that would be the EMIB, Intel's EMIB. Okay, and sometimes I've also seen this term used, 5.5D. It's basically an SoC or a packaged MCM, which basically uses both 2.5 and a 3D. Okay. So, so depending on your product, you could only use 2.5D. In some products, only use 3D, and then there is a combination. Okay. So when we are going to talk about interconnects, we are going to talk about interconnects in all these contexts. Okay. Not necessarily just 3D or 2.5D.
Hey, Srijit.
Yeah.
For what it's worth, we're seeing your presenter view, not the slideshow view.
Okay. So
it's large enough for my end. If anybody else has any issues, I suggest we keep going. Does anybody else have any issues? Or you can see the slides and everything.
It'd be nice if they could be larger, but
Okay.
Let me see if I think I can taskbar. I think we can change this somehow.
Yeah, these are swapped. That's
Yeah.
Under display settings, you're looking for.
Yeah. Let me see if there is.
If you can't, just keep moving. That's life.
The speed limit is 30 miles per hour.
Somebody is speaking. Give me a second. I could do it. Somehow I'm not able to find the proper tab.
Yeah.
Go to the pull down on display settings, not that one, the next one to the right of it.
This one, no. Start.
Display settings. Move your
It's
mouse
to the right of show taskbar.
Show taskbar.
That's where your yeah. There you go.
Is that the one? Or the
Yep,
next?
that's the one.
No. This is your video settings or displays. Okay.
Display settings.
Yeah. Something duplicate.
Just duplicate. Yeah, duplicate it. Oh yeah. There you go. Perfect.
Okay. Can you see my cursor?
5.5D.
Okay. Okay. So here we are. Okay. So we have the the 5.5D. Okay. And then there are commercial advanced packaging examples. Most of you are familiar with this, but just to recap, both Intel and TSMC and the other vendors have their own variant. Okay. And you see that what we talked about in the previous file, where there are the EMIB uses the package substrate, the CoWoS uses the interposers. Okay. And all fabs provide various variants of this. Okay. So we will keep this in mind. And one of the things that we have to understand here, and this comes from the design, is that if you use just the package substrate, the drivers used are quite different. These are essentially SerDes, watered down versions of SerDes, where we have a lot of analog components. Whereas if you use the interposer, all the products that I've worked with uses simple buffers. Okay. And this is important for us because the test of the simple buffers, test and repair of the simple buffers are considerably easier, okay, than the test and repair if you have a whole bunch of SerDes-like thing, right? The area overhead increases, okay? And of course, there are reasons why you want to use one over the other, okay? But one of the things that we have to keep in mind while you're doing the design is that the simpler the drivers, the better it is for test. Okay, so there are cost reasons why you want to go to the package and the interposer. Okay, from a design perspective, but that is also an implication of test and power. Okay, when you go from one design to the other. So just to give you an idea about the complexity, there are a range of products, okay? And this is something that I actually worked on. So I will tell you what was the problem there. So you see that, obviously there's a large number of tiles, 47 active tiles, but at the same time, they were replicated. So, you had a lot of graphics compute die, and you have a lot of general purpose compute die, memory die, IO die, and all of that coming from different process nodes. But the important thing is that if you look at the interconnects, okay, what you see here is that for the 3D, Intel was using at that time the microbump-based Foveros technology, and then they also use the EMIBs, okay, the EMIB interconnect. Okay, so in this case, it uses both. You typically don't see this, okay? You see one or the other, okay? But this was a massive design, and we saw that. Now, the point that we want to make is here is that the number of interconnects is very large, okay? And that causes a problem, right? If you, typically when we talk about IOs in our design, what happens that you have a few of them, okay, and you can really do a lot of analog testing, okay, and that is feasible. But in this case, they are all embedded in the design. You cannot touch them, right? That means the probe points cannot touch these, cannot access these devices, the output of this or the input of it to drive them. Okay, so that causes a major issue, and there's a very large number of them. So we have to come up with techniques that are called no-touch testing. Okay, so you basically have to access them through some other mechanism and understand, and determine whether they are working or not. Now, in the case of the EMIB, okay, there is you also have a pretty large number of them. Okay, the test for these two kinds of interconnects is somewhat different. Okay, the EMIB type of interconnects tests are considerably more complicated than the test for the Foveros. Okay, but the numbers are very large. Okay, so that's one thing you need to keep in mind. So I think I've made this point, right? That the receiver plays a major, the kind of drivers and receivers you use plays a major role. Okay, and what happens in that case is that for 3D and a 2.5D, you typically see the simple buffers, whereas for the one through the substrate, you see this slightly more complicated SerDes type of a transmitter receiver. Okay. Now
Okay.
yeah.
Then keep right at the fork.
Okay.
Keep right at the fork.
Okay.
Oh, sorry, Srijit. I didn't log in as an admin. Like you know what?
Southeast on I-680 South.
I'm gonna log out and then log back in as an admin, but keep going so that I can mute people.
You're on the fastest route despite.
Sorry about that.
Okay. Anyway, so just to make the difference is that, of course, you have much lower power with those simple buffers. The power is much higher. Obviously, the density is also much lower. The one that makes a lot of difference to testing is that these SerDes have analog components. And analog testing of a large number of devices is actually very, adds a lot to the complexity. Not only that, if you want to do actually monitor these for diagnosis, the amount of analog circuitry you have to add to the design becomes humongous. Okay, so this is something that will become an hindrance if you just use too many of these kind of buffers. Okay, not that we cannot handle some of it. Okay, so from a test point of view, it is better to have a design which uses simple buffers rather than these SerDes. Okay. Of course, there are other reasons. For example, power is one of the things. Density is another thing. Okay, so the first point I want to make is that when we look at these designs and do the trade-offs, okay, we should keep that in mind. Yeah. Is there a question?
No, I'm back. I'm muting all the people who are not on mute.
Okay.
Okay, I'm going to mute everybody and then unmute you. Okay, Srijit, give me a second. Okay, please go ahead. Yep, perfect. Go ahead, please.
Okay, I think we need to change things over again. So. Okay.
Yeah, all right.
Okay, can you see me? Okay, now.
Yep, I can.
Okay. Okay, so we were making this point. Okay, now let's look at the interconnect roadmap and see how it impacts test. So this is something that Intel published, and I'm using this as a reference. If you go and look at TSMC and all, Samsung, they all are very competitive products in the market for the same advanced packaging. Okay, so the important thing here is to, as we go from left to right, you see the bump pitch is decreasing. Okay, from 50 micron, then it went down to below 50. Okay, Intel is already shipping products on 25 micron. So one of the things that happened around the 25 micron is that the micro bump based technology could not be scaled down. So there was a switch over to direct copper to copper or hybrid bonding. So the intent there is to go below 10 micron. Okay, so this is a trend that we have to keep on. And the important thing that we are going to talk about is that the failure mechanisms as we go down this path is going to change. And that has an impact on the test and repair kind of features that we want to build in. Okay, so if you look at the major trends that we need to look into, okay, so one is density. And we are going from 50 micron down to 10 micron. You hear, if you attend some of these packaging things, and there is a discussion about 3 microns and 2 microns. Okay, so it is really getting dense. I think, many companies are on the verge of shipping things that are close to 10 micron. Okay, now what happens as the density becomes larger? Yeah, I mean, the positive part of it is that your die size are going to be smaller and you can accommodate a larger number of interconnects. But what happens is that the defectivity level or the amount of failures that you observe is also going to increase. And this has a major impact on both yield. And from a test perspective, we use a term called DPPM, which is basically defective parts per million that we ship to our customers. That means these are defects that we have not been able to screen out in the manufacturing test. Okay, and somehow when the customer boots up the systems, or we run this through go through this for a couple of weeks. Okay, they show up. Okay, and there is and that impacts the quality. Okay, and our customers are not happy with that. So this is essentially escapes from our test flow, and that is going to increase if you don't take care of it. The other thing that is very important is that there is an increased need for repair. If you want to get into adequate level yield, then we really need a good repair technique. Okay. The other thing that I already talked to this is the technology change. So we are changing from microbomb to hybrid. And probably we are going to use combinations of both these technologies, right? Depending on how many dies we stack. So, and I'm going to give you examples of this, that the defect profile changes, and then what kind of repair mechanisms we want to put in place also changes because of that. Okay, so now the number of interconnects, I showed you an example which had, even the forwarders 3D interconnect had 75,000 interconnects in that neighborhood. Okay, if you just go down that path and follow the product line, similar product lines, not only from Intel, from other things. Okay, I have already seen 200,000. Okay, and the count is just going up. Okay, and there is no end to how much it is, because we are essentially building. If you look at the design trends, we are not only making dies multiple dies, but also what we are doing is that we are reducing the size of the dies we are using and replicating them, right? So every time we come up with, at one time we used to use a die that probably had, 40 cores. Then and I've also seen designs where the proposal is we make them into 4 cores or 10 cores, right? And replicate them to get, better yield. Okay, so every time we make smaller dies and interconnect them, the number of interconnects is going to go up, and that has a major implication, because now what we have to do is that we have to insert the associated DFT with these large number of interconnects, and we cannot do this manually. Okay, and we also have to verify that all the DFT infrastructure is working, and once we assemble them, the DFT infrastructure is actually functioning properly. Okay, Testing such a large number of things also has an implication of test time, and we don't like this because as we increase the test time, the product cost keeps going up. Okay. Again, then again, because we are using so many, such large number of interconnects, the need to improve the yield, okay, means that we have to add higher levels of repair. That means, we cannot just tolerate one failure. We might have to tolerate 2, 3, 4, and so on. The other thing that is going to come into play is that if you look at, especially, for example, the Ponte was in the high performance computing, but if you look at the automotive and you look at anything where we turn on and off the device, so every time we boot up the device, okay, because we have to ensure that these interconnects are working. So today, if you look at the in-field test and repair, we usually, pretty much every vendor offers the in-field test and repair of memories, embedded SRAMs. Okay, I think although you are not seeing it today, in the near future you will see companies or vendors offering the feature where the interconnects have to be tested and repaired when you power up the device. Okay. The other thing that we don't often talk about is the repair cost. Repair does not come for free. Okay. And the one that you are mostly familiar with is the muxing logic. And if I want to tolerate, put in one repair or maybe two repair, this muxing logic cost of this muxing logic starts going up, not only in terms of the area that we have to add to the design, but it also has an impact on the performance. Okay, because we have to now take care of doing timing closure on longer wires. Okay, because you have to certify that in every mux configuration, your interconnect is working at the rated speed, okay, and the rated power. The other part that often is not understood by designers, especially if you look in the front end, is that the repair, once you do the test, you have to fuse the repair signature in e-fuses in your design, right? And that becomes a major problem because as the number of interconnects increases and the number of the repair and the kind of repair that we want to do increases, it adds significantly to the number of e-fuses that you have to account for in the design. And although these are and these add significantly to the cost. Okay, so that is you have to download them. So when you're powering up the system, you have to account for the time it takes to download this repair signature. That itself, it's already a significant cost for memories, and this definitely going to add to that. Now, so far as the muxing logic is concerned, we talked about the two kinds of buffers, right? The simple buffer and the more complicated SerDes. In the case of the simple buffer, you just basically have to rewire the inputs and outputs of the buffers. But in the case of the more complex things, they come in with additional inputs that we actually set during during power up. So all these analog trimming registers that are associated with these things also have to be rewired in repair. Okay, so that you have to account for the large number of amount of muxing logic that is there for those. So that is where the cost comes in addition to just the analog test. There is also a major impact on the repair cost. Okay, so and then the last point I have here is that if you look at the earliest devices that used multi-chip or chiplets, for example, in the case of Intel, it was the Lakefield, it was announced, released in the market way back. It was a handheld device, and there the interconnects are running at 300, 400, 500 megahertz, okay, no more. But if you look at more, look at Ponte or some other server products out in the market from different vendors, okay, currently they are pretty much running in the 3 to 3.5 gigahertz range. There are of course smaller, slower interconnects also, but I'm talking of the top end. Okay, and this is just going to go up. Okay, I can foresee things that are happening in the 4 to 5 gigahertz range. Now, what happens in this case is that you have this large number of wires running at a very high speed, very adjacent to each other. Okay, so what happens? There are coupling effects. Okay, that creates noise on the adjacent wires, and I will give you examples of that. Okay, that will cause failures. So depending on what data you're transmitting, at what speed and at what rate it is changing, okay, this is going to have an impact. Okay, and cause failures. Okay, so this is not a defect related failure where a particle has fallen and shorted the wires, or because of the problem with manufacturing, you have actually broken the wire. Okay, this is more coupling oriented. Okay, capacitive coupling primarily, and we refer to these as marginality. So this could also impact. Okay, you could take care of some of it in the design, but you cannot eliminate it for every process corner and for every case there. Okay, so any questions on that? So on this, maybe I can pause.
So are you reviewing these as potential causes that any standardization ever has to recognize? That's the intent of the.
Yeah. So when we talk about standardizing, okay, and I will allude to that a few things. Okay, is that these kind of failure mechanisms and repair requirements have to be part of the standard, right? So we will have to say, okay, we have to account for the kind of failures that the micro bump will be seeing, micro bump based technology will be seeing. We will have to account for the hybrid bonding failure mechanisms, and then and when we craft the tests, okay, and then do we just support 2 levels, 1 level of repair, or do we support 2 levels of repair? Okay, so we have to go account for all of those things, right? So some of the cost equations will come in from the die provider, but the standard should be able to accommodate whatever level of repair and whatever level of repair mechanism, whatever kind of repair mechanisms the die providers come up with, right? So
Got it. And out of these, which ones you think are 3D specific and which ones are 2.5D?
The last one, frequency, is both 2.5 3D, right?
Yeah.
But I think it is more for 3D.
Really? Okay.
Yeah, the reason is that it's simply because, okay, so let's say when I do 3D and 2D, let's say I have the simple Foveros micro bump, right? And the related technologies that does 3D, and they use simple buffers. They're extremely dense, right? Extremely close to each other, okay? And they are even though they are running for short distances, okay, they are not so short, right? And I'll give you one example. Okay, I have some simulation results I'll share with you. So it will happen that now what happens in, at least today, and if you look at the UCIe for the 2.5D for EMIBs, they're talking about 100 micron. If you look at the standard, that is going to go down. But if that is the thing we are talking about, the separation is large enough so that the marginalities may not be as significant, right? So one, of course, have to do your own simulation and see what if that is true or not. So the rest of them, I think hybrid is, when I say 2.5D, I'm also including the interposer based 2.5D. So I have seen both the kinds of technologies, microbump and hybrid, being used for that. Okay. So I don't think you'll see the defect profile change there. For EMIB kind of thing, which goes to the packaging, the defect profile will be quite different, right? Because they are separated out. So yeah, so those are the kinds of things we need to think about. But and if you look at the one that I brought up is the buffers, right? The complication of the buffers. In EMIB, you exclusively, you always use the SerDes kind of thing because you want to run them through higher resistive paths over longer distances, right? And even if you look at the UCIe standard, they're talking really of using that kind of drivers and receivers, in which case, the cost of repair and everything will be much higher in that case than for the simple buffers, right? So it's not very clear where the good demarcation is, right? But anyway, this is basically the thing. So yeah.
Hey, can I throw a quick question out here? Question or comment? So Ken Ferguson from Microchip, just wanted to understand when you're talking about standardization, a lot of what you've talked about has been standardizing on, the repair circuitry, having redundant and backup circuitries and muxing mechanisms in place to switch. But one of the things I'm curious, and if this is something you'd envision as part of the standards, is the capability for built-in self-repair and essentially, negotiation across the link, so that the devices on each end of the link, which may be from different vendors ultimately, are able to agree on a repair strategy. Because I don't want to have to go in and do the analysis on 200,000 separate interconnects to figure out which ones I need to do the repair on, right? I wanted to do it by itself. I think you sort of touched on that earlier, but it wasn't clear to me if that's what
you bring up a good point. So you actually hit the nail on the head. Okay. In my experience, just working within one company, you have different divisions, right? The same issue comes up, right? So what happens is that if you think about the way we have done tests so far, okay, in high volume manufacturing, if I have, my design has 5 separate dies, I go and do my scan, I do my memory BIST, I do my IO BIST, all which are specific to a die. So a die owner, a DFT owner from the die, is basically to craft their own solution, okay, and have a means to access them through something like 1838, right? So that they don't have to worry, they don't have to talk to the other die owners, or if you go to an external vendor, to the external vendor. But when we are talking about interconnect, and we are talking about test and repair, the two dies that are talking to each other using the interconnect has to agree on the test mechanism, has to agree, okay, they have to be consistent so far as the kind of test they apply, okay, the kind of hardware that is going to be in place, the way you describe them, and the repair mechanism. How do you communicate the repair requirements? Because if you think about it, only the receiving die will have the information whether there is a failure or not, and what needs to be repaired, right? And then that has to be communicated back to the transmit die. So in our standardization, that is really the main goal. We are going to say that, okay, this is how you're going to test the interconnects. This is how the various, if I have 100,000 interconnects, you cannot test 100,000 together. We will bring it down into smaller clusters. And what is the standard definition of a cluster, right? And how do you test that cluster? Okay, how do you test the clocks? How do you go ahead and repair the clock? The clock could also be failing, right? Or if there is redundancy in the clock. So all of that needs to be standardized. So that is all the part that we want to build into this standard that we are talking about. Okay, so.
Hey, Srijit, and maybe you'll touch on this later. Why is this a separate standard and not simply a property of the PHY standard in your mind?
It is at the physical level, right?
Right.
That is for sure. We are talking about now. The thing is that this cannot just be the PHY.
Okay, yeah, that's maybe.
Yeah, it cannot just be the PHY, because now we are talking about a collection of PHYs that has to be tested in a certain way and repaired, right? So some mechanisms on the PHY might have to be built into it. It might fall out from the standard, right? But you cannot be very PHY specific. But for a vendor that is providing PHYs at that level, at the physical level, right? They have to provide a mechanism to support the standard. That's what we are envisioning, right? There are some simple things that you can think about. For example, I have two SerDes, right? and both of them can be tuned independently, right? And so that they work at the rated frequency and with jitters and all of that. Right? Now, what happens is that suppose I am talking about repairing. Do I now go and have a redundant one which has yet a third register there, right? Or do we take the same settings for all the files in that cluster, right? It's an important consideration because in some cases it may work, some cases it may not work. But if it works, you have drastically reduced the area overhead, and that could be a major savings, right? So, yeah, those it cannot be very file specific, right? But the physical layer will be impacted. Okay.
Okay.
Yeah.
Thanks.
Yeah. So. Okay. Let's look at this is the microbomb thing interconnect, and the thing that I wanted to point out was that there was an old previous vision of this microbump interconnect going from 50 micron down to 10 micron. Okay, but while the technology was being developed, I think it trailed off around 30, 25 micron. Okay, and then we switched. But in this case, what really happened was that the microbump looks as follows, right? You have those copper pillars, then you put some solder on both of them, and then you attach them. Okay, and then there are other steps you do to clean this up, okay, and fill it up. So from a test point of view, this looks like simply an interconnect with a with a blob of solder in between. Okay, so so we abstract it out that level. We don't need to understand the entire processing thing. And what we want to know is that the wires going from the transmit end to the receive end are actually working properly. Okay. Now, what happens though is that this is examples of the kind of failures that we have observed in the case of say Ponte-Vecchio, right? This is a 35 micron design. So what you see here on the side here, okay, is that what you see here are that the solder from the solder bump from adjoining interconnects are smeared over, right? So because they are very, very dense, well, as a result of that, these two interconnects have got shorted. Okay. And there are various examples of this. And you can think about this is that as it becomes denser and denser, this phenomena is going to go on increasing. Okay. And then there are a couple of examples here where we show that not only two adjacent interconnects, but a number of them could get shorted in the same way. Okay. So solder bumps from edge say 3 or 4 of them, okay, could get smeared, and all 4 wires are going to be now, the other example that we have here is that these things are not forming properly, right? So basically here, this contact will not happen, okay? And as a result, you're going to get an open kind of thing. Okay, so these are 2 different kinds. And this one is an example of something that we showed. This is actually from a design. It's very design specific for a 25 micron, 3D kind of a or 2.5D with an imposer kind of a design, right? Where the interconnect was actually, the spice net list was actually extracted and a simulation was done, okay? So this is for 20 adjacent wires. And what they did here was that they toggled one of the wires, at the rated speed, and everything was held constant, okay? But you see that there are noise spikes occurring in every all the other wires, right? So these are like victims, okay? And as you go physically further away from them, the noise level decreases. But the point out here, and this is because when I went and told the product team that this could be happening, they said, okay, let's verify it, and this was a verification, right? So basically, if you have a number of wires toggling adjacent to one wire, what could happen is that the impact of the noise impact of them will be somewhat additive, right? And then the noise impact will become much higher, okay? And then as a result, the thing will basically fail, okay? So this is, you will not see them through X-rays and all, like we saw the other. So those are the examples of defects, and this is the an example of marginalities, right? Again, you should go with your own design, find out when this will be significant or not, and build the test accordingly. Okay, so that is a mistaken concept many people use, that if I have a known good die, okay, I'm going to put them together, and that is all I really need to do. Okay, what I'm basically telling here is that okay, you have a known good die, but once you do the advanced packaging, okay, the interconnects have a major failure. There's a major concern that the interconnects will not work properly. Okay, and so we will have to devise tests to test the entire package product. Okay, specifically targeting the interconnects. Okay, so that we have to we can test and repair for such failures. Okay, and improve the yield. So, this is just I will quickly go through this. So for example, the interconnects not only carry signal, they carry VCC and ground, right? And what happens is that the kind of short mechanisms that we talked about in the previous foil could also occur between interconnects that are carrying VCC and ground. Yes, we can detect them in manufacturing, okay, because there is a leakage test, the standby current will be very high, and we can reject the part. But what that does to the yield is also very significant. Okay, so this was a major yield limiter in the earliest products, and then in the test chip. Subsequently, design rules are used. Okay, and I do not know if they are adequate or not, but there is a significant effort being put in place so that we don't run too many VCC and VSS adjacent to each other, okay, and cause a yield problem. Okay, but this is something we can weed them out, okay, but we cannot repair for these failures. Okay, so the ones that we can test and repair are for the ones that we talked about in the previous falls between signal wires. And if you see that about what we saw as a defect profile was about a third of them was for shorts between signals and the VCC and ground. The others were between pairs of signal lines. Okay, and then there were quite a significant amount of failures between multiple lines. Okay, so this has an impact, right? So for example, if I just have two signal lines, okay, and if you see the UCIe standard, what they're saying is that they're going to tolerate two failures. Okay, so what this says is that you will be able to tolerate the first two kinds, but you will not be able to tolerate the failures of the third kind. Okay, which is also quite significant. So so you should read these defect profiles with that in mind. Okay, so so when we talk about the standards, we have to be able to accommodate all of them. Right? And then there are things about shorts between clocks and signals across clusters and so on. I think I'm running out of time, so let me hurry up. Okay, so that's from the microbump. Now, when you come to hybrid, things are quite different, right? What we do is that we have this pads, and then we basically place them on top of them, and then we do an annealing process, right? We place them an initial attachment at the room temperature, and then we do cycle through high temperature so that the two copper faces are annealed. Okay. Now, what happens in this case? Suppose what basically happens is that you could get contaminants that come in place in between the two dies, right? Now, one of the requirements for hybrid bonding is that you have to have a very high level clean room requirements, right? But even then, there is certain, and it becomes more and more expensive, okay, to have facilities with very, very high clean rooms, right? So as a result of that, some amount of contaminants will be there. Okay, this could be left over from previous manufacturing steps, or could be dirt in the air, right? So this is what is basically going to happen, right? you have two dies, you have those pads that are placed there, and then there is some kind of a defect, and in this case, some kind of a foreign material that could fall out there. And as a result of this, these two interconnects will not be formed properly. However, what happens to the adjacent ones? Now this thing, the top one, whichever is the top one, will become concave, and the one below will become convex, right? Or maybe the other way around, okay? As a result of this, a lot of these adjacent pads will also, interconnects will also not be formed properly, okay? So as a result of that, what you will see here is that you will see a cluster of opens forming because of one foreign particle here. Okay, so this is quite different. Okay, so what we will have to do is we will have to test. And once we test, we find that there are a couple of these wires that are not working properly. Okay, so we can, we can make an assumption that there is a certain neighborhood of wires, okay, that is not working properly. This is no longer rerouting one wire. So in this case, you'll have to reroute a whole bunch of interconnects. Okay, and the repair mechanism has to be able to account for clustered open defects. Okay, so this is quite different from the failures that we see in microbumps. Okay, so. And then, of course, there are, if you start stacking die over die, you'll see a combination of that. So everything has to, okay. In the 5 minutes or so that I have, there is a, the UCI, and I keep getting asked this question. So if you go and look at the standard, okay, they specify redundancy, but they do not say the physical layer is left really undefined. So all the test and mechanisms and all that are really needs to be put in place is not defined. Okay, so one of our things is that when we define the standards, we don't and hope standards like UCIe, AIB, and all of them will basically, and in your case, the bunch of wires should really point to a standard that is uniform across all of these interfaces that are being talked about. Okay, so and the kind of redundancy we already talked about, right? It really doesn't assumes a microbump defect profile and cannot handle clustered opens. Okay, they are using, they are motivated by the EMIP kind of technology, right? If you look at the specs and also, which is where they come from, but once you start expanding the interconnects to other things, okay, there is not much that the UCI speaks of. So I don't mean to sit here and, this is not a discussion about how bad UCI is. UCI has its own reasons to be defined the way it is defined. Okay, all I'm pointing out here is that the physical layer really needs to be looked into. Okay, and whether they fix this problem or they refer to the standards that we are developing, we will see as we go along. Okay. So the other thing that I don't have in this file is that, I saw some of the documents, they refer to P1500, 1838 and all of that. Those does not actually address the problem that I'm talking about. Okay, so essentially, based on that, we went and discussed the need for a new standard. We have a number for that, okay, 3405. And I think, as part of all the standards work that you guys are also doing, I mean, we should start, referring to this standard, because this specifically talks about the chiplet interconnect test and repair, although this is not a standard as yet, right? Work is in progress there. So rather than talking about 1838 or P1500, they do not actually, they are only test access mechanism. They do not talk about the functional wires or the functional interconnects that go between the dies. And that is what the P3405 is really meant for. Okay, so I think that is what I have. I left some time for quick Q&A. I think let's spend maybe 5-10 minutes on that. You guys have, rather than me, talking in more details about some of this work. So any questions, guys? So maybe we can, how this work relates to what you guys are doing, right? So
Everyone should be able to unmute themselves. Do you have any questions?
So I'll throw out a quick question then. This is pretty much the first time I think I've heard of 3405. How long have you guys been working on this? This is just a brand new startup standard, or where are you guys at
It
right now?
is, yeah, it is. So we were in the, as you know, what IEEE does is that it first asks you to form a study group, right? And come up with what they call a PAR, project approval request. So what we did, we started this activity sometimes early 2022. And sometimes in the around, I think the June, July timeframe, it was approved. And they gave us a number, and now we are having a work group. The work group has just about started working, right? Officially as a work group. So we have done a lot of work as part of the study group. We know what we want to try and standardize. It's still not there, but yeah, in that sense, it is pretty new. So.
And the mandate that you've got from the IEEE, this is intended to apply to a variety of different interconnect standards. I mean, you mentioned like UCIe, BO, whatever.
Yeah.
Even proprietary interconnect, like you'll have something you can design to in terms of redundancy and repair, and hopefully built-in self-repair algorithms as well.
So yeah. So basically what we want to do is that we basically want to be agnostic to the other standards, right? So we are defining the physical layer. What we are hoping is that things like UCIe, AIB, bunch of wires will say that, okay, there is a standard at the physical layer. This is how we are going to do that. Now, the question you raise is quite interesting. Today, we have a line of sight only with of the kind of repair that might be needed for these various kinds of defect mechanisms, right? And if you look at the UCI, it is saying that, okay, we will put in this kind of redundancy, right? They don't say anything beyond that. So we will, our goal is to be able to accommodate that. Now, there are more complications than that. For example, if you look at the AIB, they can say that, okay, if I have a wire that is carrying the clock, another wire that is running next to it carrying a signal, and if I want to do the repair, I should be able to swap the wire carrying a clock with a wire carrying a signal. It has major design implications. Okay, so that is allowed in AIB. It is not allowed in UCI. If you go there, they have specific redundancy for clocks, specific redundancy for signals, and so on. Okay, so we will have to accommodate all of that and make a statement. The other thing that you mentioned is actually quite important. Okay, our goal is to also standardize the test, right? The kind of test. Now, how you generate the test, we may not tell you, but whether you do it your own hardware, internal hardware, but we will tell you what kind of test is going to be applied, right? In order to carry these various defect mechanism. The other thing that we are very worried about is that the muxing scheme that is used in the two dies could be quite different. So they might have their own numbering scheme and all. So one of the things that we want to standardize is that we will allow the two dies to do whatever they want, but there has to be a way of communicating between the two dies, right? Saying that this is my repair, this is what the failure happened, okay? Which is in die 2, the receiving end. And we have to take that information and communicate it to the transmitter and ask them to do the repair. What might happen though, so we need that, but we also recognize that there could be incompatibilities. For example, die 1 could have 2 repairs. Die 1 can only repair 1 failure, right? In which case they will be compatible, but you'll have to sacrifice the yield, right? So we can only solve this problem. So these are the kinds of things we're looking into in the standard, right? How to do that. And then not only define the hardware, that's one part of it, but also define a way to describe the hardware so that design automation tools will be able to take that information and create the entire test flow for us, right? The verification and the test flow for us. Okay, so
Hey, Srijit.
Yeah.
Hey, Srijit, this is
Yeah.
James Wong here. Right,
Mm.
great presentation. All right, thanks for sharing this. And I have a question about what's for the standard here? Are you targeting on the wafer sort level or at the individual dial or at the system level, right? As the same thing?
This is all post packaging, right? This is all post
Okay.
pack. Yeah, but you know, that is you may turn around and ask, and this keeps coming up. Sometimes we have tests at the wafer sort level also. Okay, where a little part of the interconnect can be tested, right?
Right.
Yeah, but you know, those are well known, and we leave it to the die owners to do what they want with that, right? But this is primarily focused on the post packaging. So
Okay.
yeah, and you know, you know, die on wafer, wafer on wafer. You know, all of these things are quite relevant to that, and we may have to apply these at various stage of the assembly process, right? So
All right.
yeah.
Makes sense. Thanks.
What kind of deliverables do you think the standard's going to do?
The standards will specify the hardware, DFT hardware that are required in both the dies, right? And the other thing that it'll do is that it'll provide a means, at least that is our intent, is that to describe this hardware, because you know they may not be, and then so that design tools can take that description and find out whether they are compatible or not, or whether we have to sacrifice some amount of yield in order to put them together. Okay, we probably will not get 100% match all the time, right? So
yeah, I've been on P2427 for like 5 years, and it's kind of in this space and hasn't delivered anything.
Oh, okay, okay, yeah. I mean, I hope will not get down, because this I think. Okay, so if I get a sense, this is becoming so important that I think you know somebody will push us. The market will push us.
Yeah, I made proposals at P2427 for doing hardware description level defect analysis stuff. You know, so you could actually put things into models. But you know, it just got kicked out, and the whole standard's a complete hand wave job at this point.
Yeah, if you think about what is happening today, all these chiplet things is happen for, you know, all the designs that I know of is happening from chiplets that are built by the same company, right? Maybe on different processes and older and this. So they are doing whatever they want internally, right?
Yeah.
The day the market opens up, if somebody wants to take a third-party chiplet, this will simply surface. And I think that is where the market is headed. I mean, otherwise, you know, I think that is where it is headed, right? You know, we will take a IO die from some vendor, AI accelerator from somebody else, a memory things, and so on, right? I mean, that's a vision, and hopefully we will be there before that comes to fruition. So
yeah, I think it's a bit for the other standard I got involved in is, I think, P1687.2, which is like analog test.
Yeah.
Are you thinking you're going to be covering that as well?
You know, if that is a standard, we will simply refer to that, right? We don't want to create.
Well, it hasn't really done anything. It's kind of got stuck and just been circling for like 5 years as well.
Okay.
You know,
I hope we don't get down that path, you know, because you know I will lose patience, you know, because you know as an individual, you know, your interest phase, if you know, if we are going round in circles. So you know, I hope we will be able to structure this so that so far I see promising, because people also want to get, the CAD vendors are very interested in it, right? Because they see a market here and provide a solution based on a standard. So that and the market probably will pull us, okay? And hopefully, you know, we will not go down. You know, I know sometimes standards go down their own path, right? So
yeah, but you're looking for actionable things here.
We are looking for actionable things. In fact, the next meeting, which will be in the first week of January, I want to create what I'm referring to as verticals. That means, you know, these are the things that we have to discuss and finalize. Once we get a consensus on that, I think we will be in a, you know, it'll structure the the discussion, right? And without that, we will just be running around in the forest, as you mentioned, right? So, yeah. And, and we don't need to be super ambitious, right? If we get to a point where we can provide a reference manufacturing flow and a standard that is consistent with that, to me, that is a very good starting point. We may not get everything correct the first time, right? But if we have a path in which we can show, hey guys, if you do things in a certain way, you can just realize the vision of a Lego based design. That's I keep hearing, right? And then I think that would be an extremely good first step. So, yeah.
Hey, Srijit, are you, sorry if I jumped in, but
Yeah.
are you recruiting any working group members for this?
Please send me an email. You see the email there. Yeah. At this
I
point,
did.
at this point, we are not restricting anybody from participating. The only thing that we will do, once this is in full force, is that we will monitor the attendance, and if somebody is not participating too frequently, will drop. But at this point, just send me an email. I'll add you to the the meeting logistics as well as the SharePoint site, and you can attend. So we meet on Fridays, 8 a.m. to 9 a.m.
Previously.
Yeah. Like Bapi doesn't like that. So yeah, so that's when we meet. So
Srijit, I've sent you an email. I sent you an email yesterday. Do you mind checking and responding?
Okay. If you can tell me what I can't see the name.
It's Anshu.
Anshu. Okay.
Bahadur.
Okay. Okay.
Thank you.
Wait, is Eric Yan going to be in charge of monitoring attendance?
I'm sorry?
Is Eric Yan?
So in WebEx gives you an attendance list, right?
Yeah.
So we just download that and keep it. See, we'll use that stick if you see people are not participating. So this is just, we'll keep it in our back pocket, and I don't think we are going to sit down and look at attendance list and all to start with. If the work group is functioning well and people are participating, I'm assuming people have other work to do, right? So they're not signing up simply to sit there and twiddle their fingers. So yeah.
All right. Thank you.
Okay. Thank you very much, Bapi, for providing the opportunity, and let's keep the discussion going, because all of this really needs to work together, right? So yeah.
Thanks,
okay,
Srijit. Appreciate you making the time.
Bye. Bye.
Bye. Hey, JP, should we all log out and log back in, or is there not much of a meeting? Then we can just use one recording.
I think it's fine, Bobby. We don't have to really log out, log in. And do you have a recording for this? I missed this presentation.
Yeah, that was the thing. So if we hang up, and then basically the Zoom should kick out a recording, and I'll send it out.
Okay, great. Yeah, okay, let's do that.
Agenda for today. Basically, the purpose of this meeting is I wanted to see the proposal from Intel on ADI rules here.
Wait, hey, James?
They would like to propose. And then the second topic is potential for collaboration between OCP and Intel, and see how we can facilitate that.
Okay, it's a different meeting. Okay, JP, it's all yours. I guess we don't have much. I guess we should talk about the iMac guys and our thing with iMac and Fraunhofer, and trying to do a brief update on that. And that's about all I had at my end. I don't know about you.
Sorry, I've been talking in the muted mic.
Okay.
Yeah. So, Bobby, do you want to give an update, or do you want me to give an update?
You go for it, because then I'll know how much of what I was thinking stuck.
Sure, yeah. So we don't have Tarun, but I'll get started. Hello, everyone. Thank you for joining this call. This is actually the package interoperability and POC work group. And we are trying, I mean, in this work group, we are trying to develop a package interop platform, the consisting of package and the PCB, bring up PCB for it. And so what we are trying to do is the package is very specific to a test chip that we want to test the interoperability. But the board, that bring up board we are having thinking about, we want to make it as a universal test chip bring up board. So it will be useful across the people industry. And we have been looking at several vendors. Everybody has got their own bring up platforms. And it'll be good to standardize the hardware and software so it can be a lot of reuse can happen. And so we are trying to see if whom we can partner with. And there are several NXP, LBL labs already on board, and several other people are very interested in this as well. And two of our partner, I mean, the people we talked to last week, there's IMEC and Fraunhofer, both in Europe. These are big, large research institutes, and they are developing their test chiplets on their own. And they are also kind of thinking about their own bring up vehicles. So we are trying to see if we can collaborate, come up with a common industry spec through OCP, ODSA, and define that as a kind of spec, just like any other server, other projects. So Fraunhofer, they are doing a kind of more like not, this is not really a PHY test chip. There is more like an SOC kind of test chip what they are developing with the PCIe interface, PCIe and the BOW interfaces, and much more elaborate. And and we are thinking about putting some hooks for them to actually even test it with the PCIe Gen 5 interface on our DUT on our DUT board. And same with IMEC. IMEC is actually is developing a lot of chiplets for automotive applications, and they would need a bring up vehicle as well. So we are planning to kind of meet in the first week of January to define, kind of come up with a proposal or a plan or how we can address this so that it can be useful for Fraunhofer, IMEC, and lot others in the industry. Right, and evangelize this idea during this chiplet summit. So so more people on board, the more the platform gets well defined, and can be shared across and useful for multiple companies. So that's a basic idea behind this work. Bobby, is there anything you want to add?
Nope. You've covered it pretty well. Our intent is to sort of create as much of an open infrastructure as we can across here and Europe. I think the other bit of news is Trent, NXP putting in some money to get the boards going. So
Right.
that's another bit of good news. We got the first set of boards, and we still have to raise more money, but we got the first set of bring up boards, some portion of the bring up infrastructure funded by NXP.
Yeah, that's good, Bobby. And I think he is requested some budget for next year as well, correct?
Yep. And I think where we hope really to see this collaboration is on the software side. Even the hardware side will be good, but even if there's variation, to be able to create a reusable software infrastructure.
Right. And I saw some good interest from LBL, Nirmal, right, on software.
Yep. So we get LBL, IMEC, Fraunhofer. It gets to be an interesting assembly of people.
Certainly, yeah. Yeah, so I mean, we are light on agenda today. I mean, we still have to discuss with, I think probably the first week of January, we'll kick it off more in-depth discussion. And right now we have a platform definition available for our test chip bring up, but I think we're talking to more people, we can enhance it and come out with the spec. That's where we are. Any questions on this before we switch? Okay, if no more questions, actually, hi Shane. Shane, I'm just wondering if it would be a right forum, a right time for you to actually talk about your interconnect approach.
Yeah, I'd be happy to, JP.
Yeah, great. Let's do that then. This time.
Okay. Sure. Let me see. Bring up some slides here. Okay, 1 second. Here we go. Is this visible?
Yes.
Okay. Yeah, we just threw together some slides. JP had asked last week to just do a brief overview of the technology that we're developing. Just by way of introduction, my name is Shane McMahon. I'm one of the co-founders of Lux Semiconductors. Lux is a spin out of the SUNY Polytechnic Institute in Albany, New York. And we've been building the company for about 5 years now. Got about 8 full-time employees and a number of technical partners, academic labs we work with. And we're primarily funded by the by the federal government, Department of Energy, National Science Foundation, Department of Defense, and are now have just recently, over the past 6 months, have been taking orders, prototyping orders from customers. And so we're very much interested in starting to work with the commercial sector of the advanced packaging industry, which is something we really haven't done up to this point, more focused on defense. So that's why I really thought that this would be a great organization to join. Okay, so we're developing a technology that we call system on foil. The best way to think about it is it's just another material option in the world of advanced packaging. So typically, organics being the most common, silicon being the most common for advanced routing densities, and then glass kind of emerging as well. And so what we do is metal, and there's a number of just kind of high level benefits here, making it in the US better for thermals. It's a relatively stiff material, so reduced warpage. We can also make these metal substrates very thin for flexible applications. But ultimately, it gets processed in a semiconductor fab. And so we're able to pattern high density and high fidelity copper interconnects on top and bottom of the metal substrate. So kind of why metal? Looking at some of the bigger challenges in advanced packaging and the available material options and their key metrics, there is definitely some properties lacking in each material set, including metal. But we think metal has a unique value to offer, specifically in the thermal conduction, as well as kind of a stress matching material somewhere between your silicon and your organic PCB. But perhaps the biggest is going to be the through substrate vias, where the organic silicon and glass all use a kind of a copper pin or a kind of a single through via, whereas the vias that we make in the metal are naturally coaxial, and we'll get into that in a little bit, but that does increase the performance. And then just from a supply chain perspective, the materials required to go into this platform are significantly lower than those in other platforms, and we can source those in the US. And please feel free to interrupt at any time with questions. I should probably be able to get through the rest of this in 5 minutes or so. What we're showing here is just a cross section of a somewhat equivalent layer count, incorporating the difference in line and spacing of your two kind of common or emerging advanced packaging technologies, the 2.5D and the glass substrate, alongside the system on foil. And all three have cores and then either build-up layers or pattern interconnect layers on top and bottom. And what's shown here is the difference in form factor, really the significant reduction in thickness of over both platforms. Okay, so getting into a little bit more of the specifics, really this all starts by taking a sheet of metal and making it into a wafer, and specifically a wafer that has similar mechanical specs as that of a silicon wafer, so that it can be handled using automated fab equipment. It does not go into the front end of the line, but it does go into the back end of the line and receives the same type of interconnect processes that our chips would today, the higher level interconnects of our chips today, and also silicon interposers that are not using like a spin-on RDL process. So we make these bare metal wafers. We then can pattern the wafers themselves. And so what we're showing here is a through metal via. So there's a pillar of metal that is left inside of the larger metal substrate, and this donut area is filled with the dielectric to electrically isolate it. And so all your signal currents will run through the pillar, and all your ground currents will run through the grounded metal substrate. And so we show through metal vias here, but the core technology is capable of patterning any type of component in the substrate for different types of substrate functionality. Once these patterned metal wafers are complete, they then go into a semiconductor process fab in the back end of the line to receive copper SiO2 interconnects, just like a silicon wafer would go in to receive the interposer interconnects. We've run a number of wafers for various projects and customers. Right now we do 4-inch at Cornell. They have a nanofab there that we use. And we're starting to transition this process to a commercial foundry at both 6 and 8-inch. This is just one example of the wafer that we ran. This is a 3 wiring layer or 3 routing layer wafer. So a patterned substrate with 3 routing layers of copper and dielectric on top of that. And
sorry, question, Shane.
Yep.
What is the via pitch, and what are the via dimensions in the pitch?
So these are our current, and I should say future design rules, in the sense that so far we've patterned the substrate and we've patterned up to M3 here. For an upcoming project, we're going to M4, and in Q1 of next year, we'll be going down to what we call, M-1, basically a single wiring layer on the backside, and we'll be pushing to 2 backside wiring layers. So the image is kind of a future capability. Right now, it's M3 down to the pattern substrate. However, the actual design rules shown here, they will be consistent across these layers. So I think you asked for via diameter. So inside of the interconnect layers themselves, we have a min via diameter of 10 microns. The through metal vias that we show here, the min really is about 100 to 150 micron pitch. And that depends, and that's signal to signal pitch. So this signal to this signal, which in any normal substrate would include a ground pin in between it, is 150 microns, and we're continuing to try to drive that down to sub 100 microns.
I see. So it doesn't have to be symmetrical, is it? You're showing the interconnect layer on top, and then in the middle, you're showing some substrate layer, right? So, and below the substrate layer, it doesn't have to mirror what is on the top.
It doesn't have to be a mirror. We just have to consider like stress management, so we're not warping the substrate, above a certain threshold. But it doesn't have to mirror it exactly. The metal that we use is relatively stiff, and so it is much more resistant to warpage than a silicon wafer would be at an equivalent thickness.
I see. And what is the thickness of the substrate?
So our standard is between 200 and 250 microns, which is thin. However, it is mechanically rigid at both of those thicknesses across an 8-inch wafer. So it doesn't need, now if we go thinner than 200 microns at 8-inch, we start having to mount on a carrier, but we can handle the wafers without carriers down to about 200 microns.
See, and how big can you go that the substrate, the whole interconnect size, what the max size you can get?
Are you referring to like the die size? So if we pattern a design, what's the maximum kind of design size, or?
No, that you're putting chips on the top, right? That you're showing here,
Yes.
backup chips and components on the top, and how big that whole substrate can be, the XY dimensions of that.
Well, okay, if I'm understanding the question, we make 4, 6, and 8-inch, what we call metal substrates or metal wafers. And then we pattern interconnects on top and bottom, and the quote unquote die size, the package size, can be actually the size of the wafer itself, based on the lithography approach we're using. So we're not limited in the kind of package size, only limited by the size of the wafer, although we wouldn't recommend doing that for several reasons.
Okay, I see. So do you think that we can actually do something like let's say 100 millimeter or 150 millimeter by 150 millimeter, that range?
Your package size being that large?
Yeah.
You could technically do that. You would, it would be, you'd only be kind of yielding one package per run. So it wouldn't be ideal from a manufacturing standpoint, but the process itself is capable of doing that.
I see.
Wait, so I don't understand something basic. Every time I hear this, I thought you have a metal thing, won't it just be conducting signals where it's not supposed to, or did I miss that part of it talk accidentally?
Yeah, that's a good question. So if you look at this cross section here, this is kind of the patterned. This is the bare metal wafer, and then we pattern the metal wafer. Here we're just showing through metal vias. This darkness here is filled that has dielectric in it. So this metal pin is electrically isolated from the surrounding metal all the way through the thickness, and that's shown here. This blue and this kind of faded blue or gray is all dielectric, and so any signal that is routed from the top through the through metal via to the bottom is all electrically, isolated from the rest of the metal substrate. And then this first layer here on the top and bottom, it's just a dielectric layer, and then we pattern it and fill metal wherever we want to push signal through the substrate. So there's never an occasion where you'll have, signals that are supposed to be electrically isolated from the substrate being connected to the substrate.
I see. So the dielectric is in effect the substrate.
Well, really the substrate, we kind of think about it as like a metal core substrate.
Right. Okay.
And then, but you are correct in part because a certain percentage of the volume of the metal substrate ends up being a dielectric because we remove metal from the substrate and we fill it with dielectric. Overall, the large majority still is metal. However, to pattern in these components, including through metal via and others, they have to be electrically isolated from the rest of the metal substrate. And so it gets filled with dielectric in certain regions.
I presume you're filling this in and then grinding it down to make it isolated.
Yeah, we fill it in and then we have a kind of a backside removal process that we've developed.
Yeah.
Yep. And then so once the interconnects are patterned, it's just like a regular package that can receive flip chip and other die integration. One of the things we are interested in testing next year is hybrid bonding, where the planarity, the flatness of the substrate is critical, and a challenge or the possibility even for organic substrates. We go through great lengths to hit flatness specs that are on par with the silicon wafer, and so expect to be able to receive hybrid bonding processes as would a silicon interposer.
Wait, but don't you? How do you escape the challenge of the CTE mismatch between the dielectric and the copper core?
So this is actually not copper. It's a different metal. We don't publicly announce that, but we do share that with all of our customers, and it is low CTE. So it is below 6 CTE, and so and then
But
also
you need your dielectric to match that, right?
we don't really need our so the copper is going to be much higher than that. The SiO2 is actually going to be lower than that. And then we've developed our finishing development of a custom glass, actually, that is now that we need to match the metal. But the layers on top and bottom are not going to be perfectly matched to the metal, but they'll similar to a silicon interposer. The silicon interposer has a CTE that is equivalent to silicon, but it has SiO2 and copper interconnects that are not that CTE patterned on top of it, or it even has a polymer RDL that would be significantly higher in CTE than the silicon wafer itself.
I see. Thank you.
Sure.
Yeah, the another question, Shane, that here you're showing the BGA ball right below the TME substrate. Can directly, you don't need another level of packaging. You can directly mount the whole substrate onto the PCB, is it?
That's correct. Yeah. So you can see here we have C4 or BGA. So it's really entirely dependent on the customer's needs. This can be mounted directly to a board. And so like another feature that would be required for when using a metal substrate is not so much a through metal via, but just the elimination of all the metal that is underneath or above a large ball or bump, so that you don't get any capacitive coupling between a bump and the metal substrate itself. And so there are a variety of features. We don't show this one here, but you can kind of just imagine a hole is drilled through the substrate, filled with dielectric, where the bump is going to be placed. Now you're going to have this will be filled with dielectric. So locally, the bump will see a glass substrate, and then you'll pattern an RDL layer, on the bottom to connect that bump with, another portion of the substrate that has a through metal via. So yes, you can bump either C4 or BGA on the backside, and we would just drill a hole that is equivalent to diameter of whatever bump you're going to place on the backside.
No, that's very interesting. Let's say if you had to put the C4, like it's a 130 micron pitch, which is what the industry standard now, or 1 millimeter BGA pitch, wouldn't that completely, if you're removing that substrate to reduce the capacitance, would you still left with any substrate if you're putting a fine pitch C4 or BGAs?
Yeah, that's a good question. So one of the things is we have to still determine what that minimum pitch really is for the backside. It's not a problem for the top side, of course, because as you start to move to micro bumps, your capacitive coupling is going to become less and less significant. It also depends on the thickness of these layers. If you've got 4 metal layers, then you're 20 microns away. That becomes less of an issue. Also, you have most of your routing layers going back and forth between chips. So it's less of an issue on the top. Now, on the bottom, it can be an issue as you push the C4 pitch smaller and smaller and smaller. If all of those, if every IO from the chips on top and their C4 pitches need to come through the substrate, that would be an issue. But we kind of imagine fanning out those that do need to come through: power, ground, etc. And so that should kind of allow for greater spacing as you move through the substrate. But it will be, but to your point, it is going to be more of a challenge than, say, larger C4s or BGAs.
I see. So for power and ground, you don't have to remove anything, right? You can still have the substrate, correct? Because capacitance doesn't matter for power.
Yeah, that's right. And also, we just naturally operate with a grounded substrate. So you can just drop that IO down to the substrate itself and then tap into it wherever else you want. Right, because everything, the substrate is connected to itself, and it's grounded everywhere. So you can just kind of drop down and hit the substrate. We don't really show anything like that in this image, but for power, the other thing, another kind of feature that you can pattern in is like just an isolated plane. So you can kind of imagine this box here is dielectrically isolating the internal region from the external region. And the external might be all ground, where the internal might be designated for a certain voltage supply.
Mm-hmm.
So you can just kind of drop your interconnect vias down into this particular voltage plane, and then you don't really need any vias anymore. The isolation occurs at the edge, and so your bumps can just kind of touch this port. Your power bumps can just kind of touch wherever in this plane. So there are kind of ways to make the off-package routing work without eating away all of your metal substrate.
Mm-hmm. Mm-hmm. Yeah, and moreover, diodes will be at the periphery, not in the middle. So I think probably you'll get the rigidity from the middle area. And how big substrate have you demonstrated so far?
So in terms of actually patterning devices for federal contracts and customers, all of that is done on a 4-inch wafer. And most of the package sizes are 15 millimeters by 15 millimeters, although they can vary. However, we have made the bare metal wafers at 6 and 8 inch and are now developing the patterning processes for 6 and 8 inch. Now, as a company, Lux won't be doing this in-house. I mean, it will make and pattern the metal wafers in-house. That's kind of the core competency. But although we're doing the patterning ourselves using Cornell's facilities, that will be transferred over to a fab, and we're doing that now for commercial volumes. Primarily 8 inch is what we're targeting. So, but we haven't yet done full kind of prototype patterning development at 8 inch with our foundry partner.
I see. No, it's certainly very interesting, Shane, because the organic substrate stops about 100 millimeter, and it's very hard to push beyond that. And if you could actually have a solution beyond 100 millimeter, it certainly sounds very interesting. And then the other advantage is you don't have to have a second level of packaging. You can directly mount on the PCB.
That's right. Yeah, it just becomes a question of how much routing you need, and if we can accommodate all of your routing needs in our proposed kind of 6 routing layer design rule set.
Right. Do you have an RDL on below this, the 2 metal layers below?
Sorry, say that again.
Do you have an RDL layer below the stack up you're showing here?
Yeah, so we haven't done that yet. We've only done up to M3 and pattern the substrate. And so however, our initial plans for the backside layers is actually the same process as what we do on the top. So I mean, it's kind of terminology, but not so much an RDL layer. It's really like a copper damascene process with SiO2. However, we're very much interested in doing RDLs, polymer-based RDLs on both the top and bottom side, and that'll kind of just be another flavor offering of the platform.
I see. And what would be the advantage of the polymer on top? Bottom side, I understand we can redistribute, but what about top side?
Yeah, the polymer RDL process would just replace our SiO2 damascene process. Actually, I think the main advantage would be cost.
I see. So you replace the entire silicon dioxide with the polymer dielectric.
That's right.
Okay, I see. Certainly, that's certainly an advantage. Yeah.
But right now we're planarizing every single layer. So if we can get like we show here 3 micron line space resolution, and we're kind of pushing that down to 2. And for RF, that surface, that really low surface roughness, and kind of high fidelity that you get when you planarize each layer, that's really valuable as you move up in higher and higher frequencies. So the RDL will reduce cost, but it might sacrifice a little bit on those areas. And so it'll be just application dependent.
Okay.
I think the last thing I have though is
wait.
Oh,
so
yep.
no worries. I'm still like, pardon my ignorance, but what is a sort of giant, like this is like compared to interposers versus or organic substrate, what is a giant sort of why we should do this in your mind?
Yeah, okay. So I think going back up here, what you get with this is basically a substrate that has significantly higher thermal conductivity than your organic materials. So that's pretty big. Silicon interposer. So silicon is also high, relatively speaking. than organic and glass. However, as you know, as far as we're aware, all silicon interposers are mounted to organic substrates. And so there's still kind of that bottleneck, at least getting thermals down out of the package. Now you can do the thermal solutions on top of the chips, of course, but this basically provides you a built-in heat sink. That would be one. To JP's question about the size of the package, you know, we see that as well. The trend is increasing package size, and this is kind of attempted to be shown here, but that places a lot of stress at those bumps on the periphery of the package. And this material is just significantly more stiff than organic substrates, and so much more resilient to warpage as a function of temperature or stress. But I would say that the biggest thing that our customers have been interested in are the through substrate vias, and so this is the last slide I have.
Sorry, what does that phrase coaxial mean?
Oh, okay.
The word, excuse me.
Yeah. So it's kind of like all of our cabling today. You've got this, you've got a pin that carries the signal, and then you have metal.
Yeah. Okay.
And that is a fundamental difference with, you know, with other substrate technologies. They'll basically drill a hole through the substrate, and then they'll fill it with copper, and they'll place these pins. They'll place these ground pins next to signal pins in an attempt to reduce crosstalk, create 50 ohm impedance, etc. And so, although the diameter of, say, a TSV would be smaller than what we can achieve with a metal signal pin, oftentimes what ends up happening is if you really care about crosstalk, you'll have ground pins circling the single signal pin. Right. And so what ends up mattering is the signal to signal via pitch. And you kind of automatically get that with the coaxial TMV, because it leaves this ground metal around it. So it eliminates crosstalk entirely. Now you can actually just carve out this metal in between as well to kind of continue to push these signal pins closer and closer, removing that metal shield. And so your crosstalk is going to go up significantly when you do that. However, kind of the natural state here is coaxial, and so you just don't get any crosstalk through that metal, that grounded metal shield, basically. The other big difference is TDR. So with 50 ohm via design, it's very simple to do that with the TMV. You just change the ID or OD of your TMV. With this, it's like laying out ground pins around signal pins. And we've talked to multiple designers, and I guess it's quite a challenge to do that and kind of tune your vias in a way that also works with the layout that you want for all your vias. And then the other piece is loss. So when you have a single ground pin alongside of a signal pin, especially at higher frequencies, your currents are going to run at the edge of the skin of both your signal and ground. And so the amount of area that the signal is propagating through is much lower relative to over here, where all of your ground currents get like equally distributed along this outer diameter, and that also means your signal currents do the same. So that reduces loss quite a bit relative to your TSV and TGV designs. So I would say that those benefits of the through substrate via that you can get with a metal substrate versus glass or silicon is probably the most cited reason why customers are interested in using the metal technology.
Thank you.
Sure.
Very interesting, Shane. Overall, especially I'm actually see the value size that you can go. You have very stiff, and you can go beyond 100 millimeter.
Yeah, actually, we've been developing this for more like interposer applications, because we're using these semiconductor tools, and they just are inherently more capable of patterning at smaller feature sizes than your buildup layer technology. But actually, within the past like 6 months, we started having conversations with some of the government folks, particularly at the Air Force, that are in charge of kind of onshoring organic substrate supply. And that was the first thing they looked, that was the first thing they kind of saw when we presented this technology was, yeah, it probably does provide a lot of great benefits for interposer applications, but they wanted to use it as a substrate where you don't actually go from a sheet to a wafer at all. You just stay at a sheet of metal, and then you do conventional buildup layer processes on it. And it really does just become like a metal core with standard organic buildup layer processes on top of that.
Now, that's a very interesting idea. Yeah. That's in research, is it, that you're developing that process?
Yeah, we just submitted a proposal to basically start doing this. And the big thing is being able to make a sheet of metal that has the mechanical specs that we need to hit. And we've done this already at the wafer sizes I mentioned, but we haven't done that at like a panel size. And then patterning the same features at larger sizes, at larger panel sizes, is also an area of development. So yeah, we recently just submitted a proposal with support from that Air Force substrate expert, and we'll see if that comes through. But that would be the first time we're attempting transitioning this type of technology over to a panel format.
I had a question on power management ICs and things that are very noisy. Does this help a lot with reducing the noise? Just switch mode power in general.
Yeah, well, one of the things we've run some, this admittedly is an area that we're still kind of characterizing, but the power integrity, we've done a lot with signal integrity, but power integrity. I mentioned the ability to kind of carve out different areas of the substrate to be designated certain power planes. But you can also, place, okay, so you could carve out an area of the substrate. And when I mean carve out, I mean, say pattern a 50 micron line into the metal substrate that is then filled with dielectric and create this electrically isolated metal plane that you can place a chip that might be sensitive to other signals on top of. So we haven't actually done that yet, but you can kind of maybe think that that would be beneficial in terms of isolating from other signals within the package.
Yeah, I was thinking just having a solid ground plane is going to help a lot.
Yeah.
And what's it like for actually carrying power?
Yeah, we're actually we're kind of testing the limits of that right now. But one of the things I didn't show today or discuss is basically transmission lines in the substrate. So it's really a similar concept to an isolated power plane, where you bring up a voltage in that plane. But in this case, you would have, you'd actually like design a transmission, like some type of waveguide really within the substrate, that just has a lot more thickness than any of your copper layers will on top or bottom, and can support much higher currents. So we just fabricated some of these patterned substrate transmission lines and are testing them now. So I think we'll have more specificity to share on that in the coming months. But we're also just in those interconnect layers, our lines are about 4 microns of copper, 3 to 4 microns of copper. So based on the width, you can actually push a decent amount of current through those lines as well.
Okay.
So have you tried assembly of the fine pitch micro bumps on this process?
We just did actually, and that was in one of the images. We basically had we just did a daisy chain die because we completed this test structure design. So we had a daisy chain die, and the daisy chain had micro bumps that were 40 micron pitch and 22 micron diameter, and we placed that down on our substrate, and we're doing that in house right now through academic tools, but similar to the copper interconnect, where ultimately when we go to market, that'll be handled by a fab. The same will be true for the assembly piece. We don't really see us adding new value in that area of this technology. And so as long as we can provide a flat package that can be handled by the OSATs, we expect that there won't be, and of course the CTEs and so forth, but we're already kind of working through that. We expect that, similar assembly processes and bump and pitch sizes that are done on silicon interposers can be done on the system on foil platform. And the 22 micron bump diameter is just the most aggressive that we've done so far.
Mm-hmm. Yeah, very interesting, Shane.
Well, yeah, thank you, JP, and everyone for listening and letting me share what we're working on.
Hey, so do you guys have any interest in 3D printing?
Yeah, we've considered that. Actually, we were before like 2020, we were using not so much 3D printing, but it was like printed electronics. So I guess if you want to call that 3D printing, but
that's what I meant, the additive electronic stuff.
Yes, we have done that. We kind of put that to the side. We made a technical pivot like 2.5 years ago, where instead of using like printed silver traces, we pushed this into a back into the line lithography process because we saw the potential for packaging. But we still, there are certain use cases that printed interconnects could do the job without having to go through the lithography process. And so it's not our focus right now, and we're trying to kind of push all this that we've done into market first. But we're very active members of NextFlex, and they really are kind of the organizational leaders in that area. And so we do expect to kind of turn back to that at some point.
So there's this guy I met from you're in upstate New York, right?
Yes.
So this guy I met at this company called Advanced Printed Electronic Solutions. Have you run into them? By any
I don't
chance,
think I have.
they're in the Albany area. Well, you guys are in Cornell, not Albany, right?
Actually, the company is technically headquartered in Albany, but yeah, we do all of our processing work at Cornell.
Okay. Well, anyway, this guy is sort of in the same zip code, but complementary. He's looking for the additive manufacturing complement to what you guys are doing.
Okay. Yeah, we should probably talk to him. I haven't heard of the company.
And here, I think
Yeah,
it's spun off from some other company.
I was going to ask about, printing bigger 3D structures on top of the metal substrate, like antennas or heat sinks.
Exactly. So those are the type of components that we think that we think printed electronics could be well suited for, because there are some that just won't. We haven't seen, for example, the 2-3 micron line spacing of printed interconnects really shine yet. There's still a lot of challenges there. I mean, they can do it, but then reliability and the roughness of those lines, so how they perform at higher frequencies, I think there's still a lot of work to be done there. So we don't expect to change over our interconnect process to printed interconnects anytime soon. But like you mentioned, there are certain components like a heat sink, for example, that are probably much better suited for printed approaches.
I was kind of thinking that you could print the heat sink on the backside of the thing from the silicon.
Definitely.
You'd probably get very good thermal conductivity through.
And I know there's already a lot of good work going on through some of the funded NextFlex programs. They do like a call for proposals every year, and they've been doing them for about 8 or 9 years now. So there's a lot of good work that has already been conducted in that area.
You're S. McMahon at Lux Semiconductor, right?
Yes.
Okay, I'm going to introduce you guys to each other. Just you.
Appreciate that. Thanks, Bobby.
Okay, yeah, thank you, Shane. This is very, very interesting technology. Yeah, I mean, if you are successful in beyond 100 millimeter, there is a lot of cool applications for it.
Cool. Yeah. Well, thank you again. We're really ready to start working with customers and fabbing designs for them. We don't make any of our own designs or products. So it's really just trying to provide an open platform, advanced packaging technology that package designers can use from as yet another option. So thank you for the opportunity today.
Sure. Yeah. Thank you. Shane, the other thing I would like to mention is, I don't know if you've seen our interop package that we developed, 525 organic substrate with 40 by 40 millimeter. You may want to take a look and see if that's feasible in your technology. That's kind of representative of chiplet designs.
Yes, and that's so I had emailed Boppy a couple weeks ago. And then I believe you ended up sending me the link to that. So
right.
Yeah, that was me. That was kind of bugging you guys for that. And I appreciate you sending it. We've imported that into APD and we'd like to kind of replicate that actually, and using the system on foil technology. And we'd be very much interested in talking to you more about that and the willingness of Blue Cheetah and
Matrix,
to provide chips. So maybe after the new year.
Yeah, certainly we can help you design with that and see if we can get dice and similar interop packages, organic substrate you could develop on your technology. As long as you can prove that, that's wonderful. Bobby, do you have any thoughts on that?
Actually, yes, but not well formed. This is the second time we're seeing this, right? A need like Shane's. I mean, Jawad had a very similar need.
Mm-hmm.
And I think this is a this is a there's a problem worth solving, but it's not a technical barrier. It feels more like a business barrier than anything else. And I'm wondering whether we can sort of encourage some creative solutions.
I
So
think I missed it. What are you seeing as your obstacle?
well, if somebody, if Shane wants to get a couple of is it die or dice, whatever. If you want to get a few dies, it's not really of huge interest to Blue Cheetah and D Matrix to go around supporting this because there's no real upside. So if there's some way to make that happen, that other than out of the goodness of their heart, of which there is plenty. So
yeah. I think there's a chiplet design thing where you want to specify the system in a way where you can try it in different substrates with different chips and see what works best. And
yeah,
Blue Cheetah would be one supplier of like one component in that possibly. Or you may go to sort of some custom solution.
but but how do you encourage it? Because there's a second experiment we're seeing in like 2 months of this type, and there's no easy way of making it happen. So we got to figure that out.
Yeah, I mean it's part of automating the design of chiplet systems. That you can take the system level design and give it to multiple vendors and say, hey, who does this best?
Okay. Okay, yeah, let's continue the conversation maybe after the new year. Yeah. Thank you, Shane.
Thank you.
Yeah, thanks. Thanks, Kevin. Thanks, Shane. Thanks, Anshu, and JP, of course.
Yeah. Thank you, everyone. Yeah. Thank you, Bobby.
And
yeah,
thanks.
happy holidays.
Good stuff.
Bobby, we're not meeting next week, right? We'll meet in the new year, correct?
yeah. Hey, Shane, one last question for Shane. Do you have any software guys, or are you all hardware process guys?
Yeah, we don't have any true software guys. We have layout SIPI guys, and we're actually working with Siemens to start building out a PDK. But I think if you're getting towards the build up board and software for that, we don't really do that.
Yeah, no, I was thinking that you guys are probably the sort of ideal end users we should target, right, JP? Somebody like him.
Right.
With almost no software capabilities, you should be able to sort of leverage what's there.
Right. Yeah. As a end customer.
Exactly. Okay. All right. If you can make the case that Shane's company has to invest in something like this, then we're on the right track.
Yes.
Okay.
I agree.
That it's worth investing in a community effort to build this, JP. Then we're on the right track. It's not just the guys who have software people, but the people who don't have any software people on board should feel that there's a good path for them to create an infrastructure they can tap into.
Right. Yeah.
All right.
Yeah.
Thank you.
Strong case, Bobby. Yeah. Okay. Thank you,
everyone.
Talk to you then. Yeah. Bye.
Bye.
Happy holidays.
Happy New Year, happy holidays, Merry Christmas, the whole 9 yards. See you in the new year.
Thank
Bye,
you.
everyone.
Bye.